Hello, so today we are going to take a look at this problem called check if we can reach an end. And essentially the problem is we have a line that goes from 1 to n. And this line is represented with just 0 and 1 characters. And the 1 here represents position from which we are allowed to jump a certain distance, and 0 is positions where we can't jump. So we have a series of ones and zeros, like here. The position that have value 1s are position that we can jump from. The position that have value 0 are position that we can't jump from. And the goal is to go from the first position and reach the final position, right? And we are also given a distance d, let's call it d here, which represents the maximum distance we are allowed to jump by. So we can jump by less than that distance, but we can go over it. So for example, with value 4 here, that means at this position 1, we can jump either a jump of distance 4, a jump of distance 3, or a jump of distance 2, or just a jump of distance 1. So we have the interval 1 to d, that's the jumps distances that we can make. And the goal of this problem is to find the minimal number of jumps that we can do to reach n. So the minimal number of jumps that we can do to go from 1 to n, to the last position. And if there is no way to do that, we just need to return -1 if it's not possible. And one thing to note here is that the first and the last positions are always have value 1. That's guaranteed by the input. So that means we can always jump from the first position, because if not, then we have a problem and there won't be a solution. So we can always jump from the first position. So let's take a look at an example here. So we have the line is represented by these values s here. We have 8, so we go from 1 to position 8. So for example here, this position 1, position 2, position 3, 4, 5, 6, 7, 8, right? So we have 1 to 8. And the minimal, the distance we can jump from is up to 4, right? So one solution we can do is start from 1 here and say 1, 2, 3, 4, do a jump of length 4 and reach this one here, right? Reach this one, right? And then do another jump of length 4, so 1, 2, 3, 4, and reach the end. And so we only need 2 jumps actually here. If we take a look at this example where we have just length 4 and the maximum distance we can jump by is 2, there is no way to reach the end because we start from this one here. The only possible jump we can do to reach the last one is 3, a jump of 3, but we can't because d is equal to 2, so we just return -1. So this is the idea of the problem. Now let's see how we can solve it. Okay, so let's see how we can solve this, but first let's just try with some examples here. So the first example we had there was n equal to 6 and d equal to 4, right? And the string that we had there was equal to 1, 0, 0, 1, 0, 1, 0, 1, right? 4, 5, 6, 7, 8. Yep, so it has 8. So yep, let's rectify this. So this here should be 8. Okay, so let's suppose we have the line here, right? So this is 1, and then we have 2, 3, 4, 5, 6, 7, 8. And this is our position n. So the position that we can jump from, if we enumerate the values here, this is 0, 1, 2, 3, 4, 5, 6, 7, right? So what this would mean here is that we can jump at, for example, this position, of course, the first position. And then we could jump at, maybe let me pick a different color here. So we can jump here. We can jump as well at 3. Yeah, let me actually enumerate this because we are enumerating starting from 1. So let's say this would be 1, 2, 3, 4, 5, 6, 7, 8. So what this would mean here is that we can jump from here, from 4, from 6, and we can jump from 8, but yeah, that won't be useful. So what we can do here, the most optimal path we can go with is go from 1 to 4, right? The jump distance here is 1, 2, 3. right? And then from 4 we could jump 1, 2, 3, 4 and reach here. And since g is equal to 4, this one should be allowed and this one should be allowed, right? So this is the idea here. Now how can we solve this? So one simple way we can do this is kind of be greedy, right? Every time we are at a position, check like what's the maximum distance, right? We can jump by to reach a 1, right? So first we try with d, then we try with d minus 1. If we can reach a 1, then just go there, right? So basically the idea here is greedy approach. So for each position, jump by d. If we can reach 1 with it, then choose it, right? Then choose it and go from that position, right? Otherwise, we'll try, if that doesn't work, because we can't reach 1 from there, then what we can do is, if not, jump by d minus 1 and see if we reach 1 with it, right, basically. If not, go again to d minus 2 and keep going until 1, right? And so that would mean that we will always jump by the highest possible position. And then, of course, when we reach n, stop. The position n here, stop. And so here what would mean at position 1 is, okay, first let's try to jump by 4. But if we jump by 4, we will reach 5. And 5 is position 0, right? Has value 0. So that doesn't work, so let's try 3. So remember we are starting from d, which is 4. Then try 3. 3 makes us reach 1, right? And so let's go there then and start exploring from that position. So let's try again the highest possible value, which is 4. 4 makes us reach n, so we are done. We can try with other examples, but this is the main idea. And so let's try to see how we can code this up. So let's have our function here. Let's call it maybe can reach. And what we want is the current step we are at, right? So let's call that current. And we want to know how many, because remember the goal here is to return. So the goal of the function, let's write that down. So minimal number of jumps. If we can, of course, reach n. If possible. If it's possible to reach n, else we should just need to return -1. So this is what we are trying to accomplish here, right? So here, what that would mean is that actually, let's write a high-level function and then have our recursive function, because what I will try to do here is do a recursive function, because at every new step we are trying to go from that step to n, right? And just the starting point is starting from 1. So let's call this initial function here, let's call it solve, right? And solve will give us n, the point we want to reach, the distance, and s, right? And so our recursive function is going to be can reach, and that recursive function needs to have the current position, right? And the number of jumps so far, right? I'm writing my solution here in Python, and down here, like somewhere at the end there, we need to call our DFS, or we need to call our recursive function here. So our recursive function is going to start. So we are going to check if so let's say that our recursive function here will need to give us a pair, right? We either the number of jumps, or if we can jump -1, because we want to know, right? And so let's say that our function here will give us 2 values. So we'll get 2 values, right? Either jumps or can reach, and this would be our recursive function here with n, d, and s. Actually, we don't want to pass n, d, and s. We want to pass the current position at the start, that's 1, and the initial number of jumps is 0. And here we check if we cannot reach, so not can reach, so the value of that boolean is false, then we want to just return -1, right? So we handled the call, the initial call here. Now let's call the function. So the first step we need is to handle the base case when we are done, when we reach the end. So if that means that the current position is equal to n, so that means we are done, so we can just return the number of jumps and that we can reach, so we just return true. Okay, the next step is to try what we said, is trying from D and going down, right? Trying the max possible distance and just keep going down. And so to do that, we are just going to do a for loop here for I in range of, we are going to go from D going down. So in Python, I could just do that by going from 1 to D plus 1. So this would mean we will end at D, and then reversing that means we will start from D and keep going down until 1, right? And now the new position would be current plus I, right? Because this is the current jump that we'll do, right? And so for that one, we need to check if the current position plus I, it has to be less than n. We shouldn't jump like this, right? Because that would mean we'll get out, right? And so we'll check if this is less than or equal to n. And we need also the value that we reach to be 1, right? Because, for example, here, we could have jumped here, but that would be 0 and it would be a dead end. We can't move from there, so we don't want to do that, right? And so we need to also check that at position current plus I, that the value is 1. We need to do -1 because S starts, like here I represented it by starting from 1, but really in Python with the arrays it starts at 0, so we need -1 just for the position to work. And so we'll check if that value is equal to 1. Only in that case that we will go to the next recurse on that position. And so now that means that we reached a position like 4 here. We can jump there with the distance that we have, and the value is 1. So let's start from that position and try to reach the end. And so what that would mean here is that we'll recurse, right? So can reach with the new position, which is current plus I, and the number of jumps just increases by 1 because we just jumped with the distance I, and so that would mean here jumps plus 1. Okay. Now let's use these values. So this is the new value of jumps, and then we have can reach again. So let's just let's give ourselves some more space here. So we'll need two values. We'll need jumps and can reach, and this would be calling can reach with two things, with current plus I, right? And then the number of jumps, which is jumps plus 1. Okay, and now we check if only if we can reach with that position, then we are done, because that position is the highest possibility. So we don't need to explore lower ones, because that will only give us a higher number of jumps. So we can just say if can reach that means we are done, so we just need to return jumps and the value true, right? Otherwise, if we explore all the possible distances and we can't jump to reach n from there, then we could just go here and return false, and of course let's just return -1 there for the number of jumps. Okay, and that's pretty much it here. So to go over our solution here again, what we've done here is, so this is the the initial call here, we start with 1, and the number of jumps starts with the 0. And then the main idea here is this traversal here with range -1. So we start from the highest possible D, we try D -1. If D doesn't work out, we try D -2 until we try 1. If we try all of them and we can't reach N with any of them, that means it's not possible, so we just return -1. And then we have the other thing to pay attention to here is we have this here, right, where we are checking that we can reach N with that position. With the new jump, we are not going to go beyond N, and we check that the position is 1, so that it's valid essentially. And then we recurse here, right, increasing the jump by 1 because we just jumped, and going from the new position, right? And yeah, so that's pretty much for this solution. Let's code it up and run it on some examples. Okay, so I wrote down the solution that we just saw in the overview. So the function is, first we solve. We have this function solve here. And then we have a recursive function, can reach, that starts out with the current, that has the current position and the number of jumps so far. And we initialize it first with 1, that's the current position, and jumps, which is 0 initially. And then we handle the base case here. If we reach the end position, we just return the number of jumps and say that we can reach the end. Otherwise, we explore from D and we go down until 1. We are achieving that by taking the range 1 to D and then reversing that so we can go get D down to 1. And then we check if the current position plus this jump distance is less than or equal to N. That means we don't go over N, right? Because that means we will go over what we want to reach. So only if we do not go over that we continue here. And also we need the position to be 1, because if it's 0, we can't jump again. So that's a dead end, so we don't want to do it. And then we recurse on the new position and we increment the jump by 1 because we just jumped, right, with the distance I. And then we check the result if we have the variable with the new number of jumps, and then we have this variable here that just says that if we can reach the end from this new position or not. If we can, we return the new number of jumps and we return true. And if we go through all the possible distances for jumping, right, from the current position, and we can't reach the end with that, that means we can reach the end from the position current, and so we just return false, and we return -1 as the number of jumps. And that's pretty much it. And then we initialize here the call and we return number of jumps, which would be either -1 or the real number of jumps here. I have some test cases here that just help sanity check this, but it should work for every case. So all test case passes here. All of these pass here. Cool. So another solution we can think about solving this problem with is using dynamic programming, right? We can just, instead of doing this greedy approach, we can just try all possible solutions and take the minimum. So how can we do that? So with dynamic programming, we need to, of course, first define our state. So we can say that our dp of I is going to be the minimum number of jumps to reach I, right? And at that moment, well, we could have a couple of things. So this would be the state. What would be our goal function here? So goal would be, let me pick more clear color here. So what would be the goal in that condition? Then we would want the minimum number of jumps to reach N. So min number of jumps to reach N. So that would mean what we are looking for here is actually dp of N. And so with that, what we can do is we can just, we need to also actually define our base case. So what is our base case here? So our base case is, of course, dp of 0, right? So the minimum number of position jumps to reach 0, right? So that's just 0, right? And one other thing to note here is, since I'm going to start, so the problem says we go from 1 to n, but just for the sake of array, since the array enumeration starts from n, starts from 0 to n minus 1, I'm going to modify it slightly, just the representation, so that is 0 to n minus 1. So what that would mean here is that our representation here is going to be slightly different. So we are going to say this is minus 1, and that way we need to go from 0 to n minus 1, right? And then what we need is also our recurrence relation as part of our definition for the dynamic programming solution. So what is our recurrence relation? So for dp of some value x, right? Or let's say, so dp of some value x plus some distance, right? Let's call that maybe dist here. So this is dist, of course, has to be less than or equal to d. Then it's just the minimum of that, right? Getting to x, right? Plus 1, because the jump here would be a jump of dist, right? And whatever the value was there before at that position, right? So this would be our dp relation, right? Basically what this says here is that let's say we were at a position like this, right? So now we were at x here, right? And this is x plus distance. So it's either like reaching this one from another position, maybe here, or maybe another position like this, or reaching it with distance, this one, right? And so we would have already, we need to explore all of them and then pick them in each time and then try every jump, right? Try every possible jump, right? So what that would mean here, so that would mean here dist, for dist, try all possible jump distances, right? Which would mean here that we will try 1 to d, right? And yeah, so that's pretty much it for this. Now for the recurrence relation, now let's see how we can do what would be our order of iteration. These are usual things that we should think about for DFS. And in our case here, well, we know that we need to try all the x's, right, from 0 to n minus 1, right, to reach n and give the value of that. So we know that we need 4x in range of 0 to n. And we know that for each position, we need to try all the distances, right? So we need to try for each position. Let's write that down here. So for each position, try, we know that we need to try from 1 to d, right? Try jumping by d, try jumping by d minus 1, try jumping by d minus 2, and try jumping by 1, right? And so what this would mean here is that, but we only can jump from position 1. So that's the caveat here. Can only jump from a value 1, right? So we need to check here. So what that would mean that here we need to check if the element at position x is equal to 1. Only in that case that we will explore all the jumps. So we do for let me write it in a different color here for clarity. So so that would mean here for distance in range of, the range is from 1 to d, right? So we'll try all these distances, and then we'll plug in this condition, but this one we can't use it only if, again, we have another condition, which is we can't go over n minus 1, and the value that we go to has to be 1 again. The value that we jump to, right, regardless of the jump distance, has to be 1. So here we need to do if x plus distance less than n, and the value at position x plus distance has to be equal to 1. Only in that case that we, if we call this 1, that we plug in recurrence 1 here, right? And that's pretty much it. And then at the end, so what we return at the end can be just dp of n minus 1. With just one caveat is we need to distinguish if we really did populate dp of n minus 1 or not. So that would mean here that our initially, let's just fill our dp with infinity values, right? Which will allow us here, all of them, infinity is bigger than anything. So when we do min here, whatever the value is we find, it will take over. And that's what we want. Except if we don't reach n minus 1 at all, then the value is infinity. So dp of n minus 1, if the value is different than infinity, let's call this maybe env variable, we'll define it later. In Python, we can use float infinity. Else, we just need to return minus 1 because we didn't reach it, right? So with this, our solution should be clear, and we can start writing the entire algorithm here. So let's write it down. So the first thing is, let's define the function. Let's call it maybe solve, right? With n and d and s. Okay, and we need to define our dp, and we said initially our dp is going to be filled with infinity values. So what that would mean is, let's just define a variable here in Python. We will call it env, which would be just a float of infinity. And then we need our dp solution, so our dp array here that we'll define as env, right? Let's multiply it by n plus 1. Yeah, just to give us some space to reach n. We could also, yeah, pretty much. So we have infinity initially for every position. And then our base case, which we said here, is 0 because the minimum number of jumps to reach 0 is 0. And then after that, we need to start our iteration that we mentioned here. So that would mean we need to go for x from 0 to n, right? Like here. So for x in range of 0 to n, what we will need is to check, same way we did here, that the value is 1, right? So if the value at that position is equal to 1, then that means we can do our loop here for the distances. So we do for distance in range of, here we are going to try everything, so we don't have to start from the highest distance value. So we go just with 1 to d, and then we check if we can do that jump using the conditions that we have. So if that x plus the distance is smaller than n, so that we don't go over the position n minus 1, and the value at position x plus distance is equal to 1. So one thing to call out here, I'm not doing minus 1 because I converted instead my scale from 1 to n to 0 to n minus 1. So the values, the indices are correct there. So only if this condition is correct, I can use my recurrence relation, which is this one here. So let's define that one. So that recurrence relation says that x plus dist is going to be equal to the min of x, the min of whatever value was there before, and the new value that we just obtained, which is dp of x plus the jump that we just did with the distance d. And then at the end, once we finish the loop, here we can say return dp of n minus 1 if we did reach it, which means the value is different than infinity. Otherwise, we just need to return -1. And infinity, we just define it as float minus infinity here. And that's pretty much it for this solution. So if we try to just think about the time complexity here, we can see that, well, we did O of n here, of course, and then we have O of d here. So at most, even though we don't do it for every position, we just do it for those that are 1, at most here, our time is O of n d, which seems reasonable. Yeah, so that's it pretty much for this. Let's write it down front on our test cases and make sure it passes. Okay, so I have here the solution that we just saw in the overview. So it's pretty simple. We have the dynamic programming array, DP array here, initialized with infinity values. We set the initial value to 0, and then we go through all the possible x values from 0 to n-1. And then if the position has value 1, then that means we can try to jump from there. And so we try different steps, or as we called it in the overview, dist, and from 1 to d, right? And then we go here, and if doing that jump won't go in n-1, and that position is 1, right? Because we don't want to go to a dead end position again. If those two conditions are valid, then we do our recurrence relation here with dpx plus distance is equal to dpx plus 1, because we just did one jump, and we minimize over whatever previous value we had there. And then at the end, if we return the value at position n-1, if we were able to reach it, which means the value is different than infinity, otherwise we return -1. Okay, so let's run this on a couple of examples, just make sure it passes. And our test cases pass here. So yeah, so that's pretty much, I think, for this solution. We have two solutions here. One of them is kind of a greedy one and recursive in a way here, and the other one is using dynamic programming. Yeah, so thanks for watching, and see you on the next one.